There is a mountain beneath the ocean right now. Not a small one. A mountain so tall that if you placed it on land, it would stand higher than Everest. You have never heard its name. Almost no human being has ever seen it. And it is absolutely teeming with life. There are more than 100,000 mountains like this beneath the world's oceans. 100,000. And we have explored, in any meaningful detail, fewer than 300 of them. Tonight, we descend. We will travel through the formation of these mountains, born from fire at the bottom of the sea. We will witness the extraordinary life that clings to their slopes, coral gardens 600 years old, creatures that have never once seen sunlight. We will follow the whales and the sharks that have been using these mountains as highways for thousands of generations. We will visit an expedition that found 100 species, never seen, never named, in less than 30 days. And we will confront the uncomfortable truth about what is being planned for these mountains right now. Tonight, something is going to change about the way you see the ocean floor. Stay with us until Chapter 7. Shh! What mining companies are preparing to do to these mountains, and what it means for the phone in your hand, Jimeo, is something every person on Earth should understand. If this documentary helps you rest, helps you learn, or simply helps you feel the quiet wonder of the deep ocean tonight, please consider subscribing. This channel exists to bring the hidden world beneath the waves into your home. And we are just getting started. Now, let us go down. Chapter 1. The Hidden World Beneath the Waves. There are things on this earth that we walk past every day without ever knowing they exist. Gish. A street, a building, a face-in-a crowd. We move through the world assuming we understand its shape. We have maps, we have satellites, we have technology that can photograph a single leaf from space. And yet, beneath the surface of the ocean, which covers 71% of this planet, there is a world we have barely touched. A world of mountains, ranges, peaks, valleys carved by forces older than any living thing on Earth. We call them seamounts, and they may be the most extraordinary and most overlooked feature of our entire planet. By scientific definition, a seamount must rise at least 1,000 meters from the ocean floor. 1,000 meters. That is taller than the tallest building ever constructed by human hands, by a considerable margin. And that is simply the minimum. The threshold to even qualify. Many seamounts rise 2,000 meters, 3,000, 4,000. Some, when measured from their base on the ocean floor, stand taller than any mountain on the surface of the Earth. Mauna Kea in Hawaii, when measured from its base on the ocean floor, stands nearly 10,200 meters tall. Everest, from base to summit, is 8,849 meters. Mauna Kea wins by more than a kilometre. And Mauna Kea is just one seamount. One of more than 100,000. 100,000 underwater mountains. Let that settle for a moment. If you visited one seamount every single day, without rest, without pause, it would take you more than 270 years to see them all. And that is assuming every single one had already been found. They have not. Even today, with satellites, with sonar, with the most advanced ocean mapping technology ever built, scientists estimate that the number of seamounts on Earth may be significantly higher than 100,000. Some estimates suggest the true number could be closer to 300,000. Mountains beneath the ocean, hidden in plain sight. Most of them never visited. Most of them never even mapped in detail. We have better maps of the surface of Mars than we do of our own ocean floor. You might wonder, reasonably, how this is possible. We live in an age of extraordinary technology. We have mapped every continent. We have sent robots to the edge of the solar system. We have sequenced the human genome. And yet here, on our own planet, beneath a surface we have sailed for 10,000 years, entire mountain ranges remain unknown. The reason is both simple and humbling. The ocean is deep, almost incomprehensibly deep. The average depth of the ocean is 3,800 meters. At that depth, the pressure of the water above is so extreme that it would crush an unprotected human body instantly. Satellite imaging cannot penetrate seawater. It bounces off the surface. It tells us almost nothing about what lies below. To map the ocean floor, ships must use sonar. And pulses sent downward, bouncing off the bottom, returning to the surface. It works, but it is slow. Enormously, painstakingly slow. A single research vessel can map a strip of ocean floor roughly 30 kilometers wide. The ocean covers 360 million square kilometers. The mathematics are unforgiving. As of today, less than 25% of the ocean floor has been mapped in meaningful detail. The rest is guesswork, outlines, rough shapes in the dark. The seamounts we do know about span every ocean on Earth. Some stand alone, solitary peaks rising from the abyssal plain, isolated by thousands of kilometers of open water in every direction. Others form chains, long arcing lines of the mountains stretching across entire ocean basins. The Emperor Seamount chain in the North Pacific stretches nearly 6,000 kilometers. The New England Seamounts in the North Atlantic extend more than 1,000 kilometers from the edge of the American continental shelf. The Salas y Gomez Ridge in the South Pacific connects the coast of Chile to Easter Island. These chains are not random. They are the fingerprints of geological time, the record of where the Earth's tectonic plates have been, a map written not in ink, but in stone and fire and the slow patience of millions of years. Of the seamounts we have identified, a remarkable number have never been given a name. They exist in scientific databases as coordinates, numbers, grid references on a chart that no one looks at very often. In 2024, during a single expedition to the Salas y Gomez Ridge, scientists discovered 4 seamounts that were not on any chart at all. Mountains of volcanic rock rising thousands of meters from the ocean floor. Previously unknown to science. Found by accident. One of them, when properly measured for the first time, turned out to be nearly 1,000 meters taller than any previous estimate. A mountain the height of 3 Empire State Buildings stacked on top of each other, and we had simply been measuring it wrong for decades. A seamount rises from the soft sediment of the deep ocean floor. That sediment, fine, muddy, featureless, covers most of the ocean bottom. It supports certain kinds of life, but it is, in ecological terms, a desert. A seamount changes everything. Its slopes are hard volcanic basalt, rock, solid, ancient. And on that rock, creatures can anchor, coral can root, sponges can hold, an entire architecture of life can build itself layer upon layer, species upon species, on a foundation that the surrounding oceans simply cannot offer. But that is a story for the next chapter. Because first, we need to understand where these mountains came from. How something so vast, so ancient, could rise from the bottom of the sea. And why the story of their birth, Ahomser, begins not with water, but with fire. Before we move on, pause for a moment and consider this. Everything we have just explored, the scale, the numbers, the unnamed mountains in the dark, all of this describes a world that has existed for tens of millions of years. A world that was here before humans, before mammals, before the dinosaurs walked the earth above. And in all that time, through all those millions of years of silence and darkness and cold, a life found its way onto these mountains. Life that is unlike anything we see anywhere else on the planet. Life that should not, by any ordinary measure, exist. But before we meet that life, we need to go further back. To the very beginning, to the crack in the ocean floor, to the column of heat rising from the mantle, to the moment, billions of years in the making, when fire met water, and a mountain was born. Chapter 2. Born of fire. Every seamount begins with violence. Not the slow, quiet kind of change we associate with the ocean. Something older. Something primal. Deep beneath the ocean floor, far below the creatures, the coral, the cold dark water, the earth is alive. Its mantle moves slowly, constantly, churning with heat left over from the formation of the planet itself from 4.5 billion years ago. In certain places, that heat concentrates. It builds pressure against the underside of the ocean crust. And then, at some point, in some place, the crust gives way. A crack. Just a fracture. A seam opening in the rock. And through that seam, magma rises. It meets the ocean water and the reaction is immediate. The lava cools in seconds. It hardens into black volcanic basalt, dark, dense, crystalline. And where one layer cools, and another pushes through beneath it, layer upon layer, flow upon flow. This is how a seamount is born. Not in a moment, not in a century, in millions of years of relentless, patient accumulation. Seamounts are born in two different ways. The first way is along mid-ocean ridges. These are the great underwater mountain chains that run through every ocean on Earth, the seams where tectonic plates pull apart from each other. As the plates separate, magma rises to fill the gap. New ocean crust is born. And along these ridges, volcanic activity is intense and continuous. It's formed here in great numbers. The second birthplace is more dramatic still. Hotspots. A hotspot is a fixed point of intense heat in the Earth's mantle, where an unusually powerful column of heat pushes upward through whatever crust sits above it. Unlike the mid-ocean ridges, hotspots do not move, but the tectonic plates above them do. Slowly, at roughly the speed a human fingernail grows, the plate slides across the hotspot. And as it does, a chain of volcanoes is born, each one growing over the hotspot, then moving away, going cold, and subsiding. The Hawaiian island. The most famous example of this process on Earth The big island of Hawaii sits directly over the hotspot right now, actively volcanic, still growing. Maui formed there, then Oahu, then Kauai, each one older, each one further northwest along the chain. And beyond Kauai, continuing northwest for nearly 6,000 kilometres, lies the Emperor Seamount chain. The older islands, worn down by waves, submerged beneath the sea, return to seamounts. The chain is a timeline written in stone, each seamount a chapter in a story that stretches back 80 million years. Some seamounts grow large enough to reach the surface. They break through the water. They feel sunlight. They become islands. But the tectonic plate keeps moving. The hotspot that fed the volcano is left behind. The eruptions slow, stop. The island begins to erode. Waves attack its edges. Rain carves its peaks. Over millions of years, the island shrinks. Its summit drops toward the waterline. And then, one day, it disappears below the surface. But it leaves something behind. Where the waves once carved its summit flat, a platform of rock remains, horizontal, level, as though cut by a blade. Scientists call these flat-topped seamounts guyots. They are ancient islands, fossilized memories of land that once stood in the sunlight, now resting in permanent darkness hundreds of meters below the surface. There is something quietly moving about a guyot. A flat summit that was once a beach, where waves once broke, where, perhaps, birds once landed. Now cold, dark, covered in coral and sponge and the slow accumulation of marine snow drifting down from a surface it will never see again. The volcanic basalt that forms seamounts is not just geologically interesting. It is ecologically critical. The deep ocean floor is mostly soft sediment. You cannot anchor to sediment. You cannot root into it. A coral trying to establish itself on soft mud finds the foundation shifts and collapses and nothing holds. But basalt is different. Hard, solid, dibble. A coral polyp landing on a basalt slope finds purchase. It holds. It grows. A sponge anchors. And where one organism establishes, others follow. The oldest seamounts on Earth are more than 100 million years old. When these mountains first rose from the ocean floor, dinosaurs were alive. The continents were arranged differently. The Atlantic Ocean was still young and narrow. No human being had yet evolved, nor would one for another 99 million years. And yet these mountains stood then as they stand now. Patient, unchanging in any timescale a human mind can truly grasp. There is a particular seamount in the North Pacific, part of the Emperor chain, that is estimated to be 82 million years old. It has outlasted every species that ever lived on its slopes. Entire evolutionary lineages, born, flourishing, extinct, while the mountain simply waited. It will outlast us too. The mountain is built. The volcano has gone cold, and now it sits, alone in the deep ocean, a tower of basalt in an empty sea. But something is about to happen. Something that has nothing to do with geology. Something invisible. Something that begins the moment that mountain rises high enough to interrupt the flow of the deep ocean currents. Because a seamount does not just sit in the ocean. It changes the ocean, round it, above it, for hundreds of kilometers in every direction. And what that change creates, in the water, in the current, in the chemistry of the sea itself, is something that makes life possible in one of the most barren places on Earth. That story is next. Chapter 3: The Invisible Force. Picture the open ocean. Not a coastline. Not a reef. Not the shallow turquoise water of a tropical bay. The real open ocean. Blue in every direction, flat to the horizon. No land, no feature, just water, stretching away in every direction for thousands of kilometers. Now go deeper. Down through the sunlit surface layer, down through the twilight zone where the light fades to nothing, down into the deep ocean, cold, dark, still. This is what most of the ocean floor looks like. A vast, flat, featureless plain of soft sediment. Almost nothing moves here. Almost nothing lives here. The deep ocean in most places is as close to a true desert as anywhere on Earth. Food is scarce. Current is minimal. Life gradually, but thinly, patiently, clinging to whatever drifts down from above. Now, place a mountain in the middle of that desert. Watch what happens. The deep ocean is not still. Even in the darkness, currents move. Slowly, horizontally, great rivers of cold water flowing through the abyss. These deep currents carry something precious. Nutrients, nitrates, phosphates, iron, the chemical building blocks of life, locked away in the cold, dark water, moving slowly and going nowhere useful. Then the current hits a seamount. It cannot go through it. It cannot go under it. It must go around it or over it. And as the current is forced upward along the seamount slopes, it carries those nutrients with it. Up, toward the surface, toward the sunlight. This process is called upwelling, and it transforms the ocean above a seamount completely. Where there was nothing, there is now food. Phytoplankton bloom in the nutrient-rich water above the summit. Zooplankton gather to graze on the phytoplankton. Small fish gather to feed on the zooplankton. Larger fish gather to feed on the smaller fish. And at the top of this sudden, unexpected food chain, sharks, tuna, billfish, seabirds diving from above. An entire web of life, assembled above a mountain that none of these creatures can see, drawn by the invisible chemistry of upwelling water. Above some seamounts, something even stranger happens. The Earth rotates. When a current encounters a seamount and is forced upward, the rotation of the Earth causes that rising water to spin. It creates a closed eddy. A column of rotating water, trapped above the seamount summit, circulating, going nowhere. Scientists call this a Taylor cap. A Taylor cap acts like an invisible dome over the seamount summit. Water enters it, but does not easily leave. Nutrients are concentrated within it. Plankton accumulates. And anything small enough to be carried by the current, larvae, eggs, juvenile organisms, becomes trapped inside. Protected, or retained, held above the seamount for days or weeks, long enough to feed, to grow, to develop. A seamount summit under the influence of a tailor cap becomes a nursery, one of the most effective natural nurseries in the ocean. Research published as recently as 2025 confirmed what marine scientists had long suspected. Seamounts are measurable hotspots of biodiversity in the open ocean. More species, more individuals, more interactions, more life, in every measurable sense. The seamount does not create this life from nothing. It concentrates it. It gathers it. It gives the scattered, dispersed organisms of the open ocean a place to converge. An oasis. In the middle of a desert that stretches for thousands of kilometers in every direction. Humpback whales congregate around seamounts during migration. Not randomly. Consistently. Generation after generation, returning to the same peaks, the same ridges, the same underwater summits where the upwelling is rich and the food is reliable. Sperm whales dive alongside seamount slopes, using their extraordinary sonar to map the mountain below. Blue sharks, hammerheads, great white sharks, all have been tracked following seamount chains across ocean basins. Even seabirds respond. Albatross, those extraordinary wanderers that spend years at sea without touching land, have been observed congregating above seamount summits. The seamount connects every layer of the ocean simultaneously. From the birds at the surface, to the sharks in the middle water, to the coral gardens on the slopes below. So now we know what a seamount does to the water around it. We understand the upwelling, the tailor cap, the gathering of life from every layer of the ocean. But we have not yet descended to the mountain itself. In the next chapter, we go deeper. Down past the sharks and the tuna, down past the twilight zone, down to the slopes themselves, where the coral gardens have been growing for centuries, where glass sponges filter the cold current, where creatures cling to ancient volcanic rock in total darkness and have been doing so for longer than any human civilization has existed. Something extraordinary is waiting for us down there. Something that, once you have seen it, changes the way you think about the word alive. Chapter 4. The Ancient Highways. Imagine you are a humpback whale. You weigh 40 tons. You're 30 meters long. And every year, without fail, you travel thousands of kilometers across the open ocean. From your feeding grounds in cold polar waters, to your breeding grounds in warm tropical seas, and back again. No map, no compass, no GPS. Just the ocean, and something inside you that knows the way. For decades, scientists wondered how large migratory animals navigated the open ocean with such precision. The Earth's magnetic field plays a role. Ocean temperature gradients play a role. But there is something else. Something that researchers are only beginning to fully appreciate. The seamounts. A seamount rising thousands of meters from the ocean floor creates a physical landmark. Not a visible one. The deep ocean is lightless, but a detectable one. the gravitational signature of a large seamount is measurable. Its acoustic presence, the sound of upwelling water, and of biological activity concentrated around its slopes, carries for hundreds of kilometres. Its magnetic properties, volcanic basalt has a distinct magnetic signature, can be sensed by animals capable of magnetoreception. Whales are almost certainly capable of magnetoreception. So are sharks. So, researchers now believe, are many other large migratory fish. The seamount chain is not just a series of underwater mountains. It is a navigation system. Ancient, reliable, used by creatures that evolved alongside it over millions of years, long before any human thought to draw a map. Humpback whales have been documented congregating around seamounts on every major ocean basin. The New England seamounts, stretching northeast from the American continental shelf WSD, lie directly along one of the most heavily used humpback migration corridors in the North Atlantic. Research vessels following tagged whales have recorded animals pausing at seamount summits, feeding in the upwelling, resting in the calmer water above the peak, sometimes remaining for days before continuing their journey. Sperm whales show similar behaviour. These deep-diving hunters, capable of descending to more than 2,000 metres, use seamount slopes as hunting grounds. A sperm whale that finds a productive seamount will return to it, year after year, decade after decade, passing the knowledge of its location to the next generation. There are seamounts in the Pacific that have almost certainly been visited by sperm whales for thousands of years. The mountain does not know this. The whale does not think about it. But the relationship, ancient, silent, reliable, continues. White sharks tagged in the eastern Pacific have been recorded following the seamount chain between the California coast and Hawaii with extraordinary precision. Moving from peak to peak, and pausing at each one, then continuing. The route, nicknamed the White Shark Cafe by researchers who first documented it, follows seamounts so consistently that scientists initially wondered if the sharks were using them as a map. Hammerhead sharks aggregate around seamounts in such numbers that certain peaks have become famous among divers and researchers. Cocos Island in the Pacific, the Wolf and Darwin seamounts in the Galapagos, dozens, sometimes hundreds of hammerheads circling a single seamount summit. Now zoom out. Not just to individual whales and sharks following individual chains, but to evolutionary time, to millions of years. The deep ocean is vast. Between any two seamounts, there may be hundreds or thousands of kilometres of open water. For a whale, this is a single day's travel. For a fish, perhaps a week. But for a larva, a microscopic juvenile organism drifting in the current, the crossing of 1,000 kilometres of open ocean seems impossible. And yet, the same species of deep-sea coral appears on seamounts in the Atlantic and the Pacific. The same species of squat lobster colonizes seamounts separated by entire ocean basins. The explanation is what scientists call the stepping stone model. A larva hatches above one seamount. It drifts in the current, carried toward the next seamount in the chain, where the upwelling concentrates food, where the hard substrate offers anchorage. Generation by generation, seamount by seamount, species spread across ocean basins over geological time. Modern technology is finally allowing scientists to trace these connections. Environmental DNA, tiny fragments of genetic material shed by organisms into the water, can now be collected from seawater samples and analysed to identify which species were present. Damn. What researchers are finding confirms what the stepping stone model predicted. Seamounts are not isolated islands. They are nodes in a network, a living, dynamic, biologically connected system that spans the entire ocean. Damage one node, and the effects ripple outward. The network weakens. The connectivity frays. The network is real. The highways are ancient. The whales and sharks and drifting larvae have been using them for millions of years. But we have still not landed. In the next chapter, we finally arrive. We descend to the slopes. We enter the coral gardens. We meet the creatures that live on these mountains permanently, in the cold, in the dark, in the silence. One of them is 600 years old. It has never seen light, and it is one of the most important organisms in the deep ocean. We will meet it next. Chapter 5. Cities in the Dark. We are descending now. Past the surface. Past the sunlit zone where the water is warm and blue and familiar. Past the twilight zone where the light fades from blue to grey to nothing. The temperature drops. The pressure builds. The darkness becomes complete. And then, in the beam of a research vehicle's light, something appears below us. Not the flat grey mud of the abyssal plain. Something different. Something rising. Dark volcanic rock. And on it, colour. The first thing you notice on a seamount slope is the coral. Not the coral you might picture from a tropical reef. Not the bright oranges and purples and yellows of shallow water species. Something quieter, older, more patient. Shh. Cold water coral grows in the deep ocean where no sunlight ever reaches. Unlike its tropical cousins, it feeds entirely by filtering particles from the current. And it grows. Slowly. Extraordinarily slowly. Some species grow at just 1 millimetre per year. 1 millimetre. A coral branch the length of your forearm may have taken 200 years to reach that size. A coral tree tall enough to shelter a school of fish may be 500 years old. On Davidson Seamount, off the coast of California, scientists have recorded coral specimens estimated to be over 800 years old. Ish. 800 years. This coral was alive when the Mongol Empire was at its height, when the first universities in Europe were being founded, when the word seamount did not yet exist in any human language. A cold water coral thicket is not just a coral. It is a structure, a three-dimensional architecture that transforms a bare slope of volcanic rock into something resembling a forest. Brittle stars are among the first to exploit it. These relatives of starfish, with their long, flexible arms, climb the coral branches to get themselves off the muddy seafloor. Elevated above the sediment, they extend their arms into the passing current, catching food particles with tiny tube feet. On some seamounts, brittle stars cover the coral in such density that the underlying structure is almost invisible. A coral tree draped entirely in writhing arms, each one feeding independently, the whole assembly pulsing slowly in the current. Tiny crustaceans shelter in the spaces between coral branches. Juvenile fish use the thicket as a nursery. Sea urchins graze on algae growing on the coral surface. Polychaete worms thread through the gaps. each species creating conditions that allow the next species to establish. Layer upon layer of life, built on the foundation of a coral that has been growing since before your great-great-grandparents were born. Alongside the coral, and in some places instead of it, grow the glass sponges. These are among the most extraordinary organisms in the ocean. Their skeletons are made not of calcium carbonate, but of silica. Biological glass. The structure of a glass sponge is a lattice of interlocking silica fibres, geometrically precise, structurally elegant, and in the beam of a research vehicle's light, luminous. They glow. Not from bioluminescence, but from the way their silica fibres conduct and scatter light. A glass sponge field on a seamount slope, illuminated by an ROV, looks like a field of lanterns. Some glass sponge species can grow to more than 2 meters tall. Taller than a person, standing in the cold dark current, filtering thousands of litres of seawater every day. Squat lobsters are among the most abundant residents. Small, typically 5 to 10 centimetres long, but present in extraordinary numbers. On productive seamounts, they cover the rock in dense carpets, orange and red and rust-coloured, thousands of individuals packed onto a single outcrop. Cusk eels drift along the slopes, elongated, pale, and moving with an unhurried sinuosity that seems almost languid in the cold water. Dumbo octopuses, named for the large ear-like fins they use to propel themselves, hover near the seamount summit, flapping slowly, drifting, their translucent bodies ghostly in the darkness. They are among the deepest living octopus species on Earth, found at depths of up to 7,000 metres. The permanent residents of the seamount are joined regularly by visitors from above. 6-gill sharks descend from the mid-water to patrol the seamount slopes. Among the most ancient shark lineages on Earth, their body plan essentially unchanged for 200 million years. Ghost sharks drift past looking like creatures from another world entirely. Their large green eyes, their spotted their long whip-like tails trailing behind them. They split from the shark lineage over 400 million years ago. They are something older, something that has been swimming in deep water since before the dinosaurs. And occasionally, descending slowly from above, dwarfing everything around it, a sperm whale. Its sonar clicks echoing off the volcanic rock, mapping the mountain, hunting the squid that gather in the productive water above its peak. Davidson Seamount, located off the coast of central California, is one of the most thoroughly studied seamounts on Earth. 6 major scientific expeditions have explored it. Together they have recorded more than 60,000 individual species observations. Scientists who have reviewed the data from Davidson consistently use the same word: overwhelming. Not in a negative sense. In the sense of abundance so far beyond expectation, in a place where abundance should be impossible, that it forces a reconsideration of everything you thought you understood about the deep ocean. Yet, Davidson is one of fewer than 300 seamounts that have been explored in any meaningful detail. 300 out of 100,000. The other 99,700 are waiting. In the dark, unknown, unvisited. The darkness does not mean emptiness. It never has. It means unseen. Rest now in the image of that coral garden. 600 years old, swaying in a cold, dark current, covered in brittle stars reaching upward in the dark. Now, hold that image. Because in 2024, scientists sailed to a seamount chain they had never explored, what they found in less than 30 days was not interesting. It was historic. 100 species, never seen, never named, never known to science. Found on seamounts that had simply been waiting, patient, dark alive, for someone to finally come and look. That discovery is next. Chapter 6, 100. New species. In January of 2024, a research vessel left the port of Valparaiso, Chile. On board, a team of marine scientists. Their destination, the Salas y Gomez Ridge. This ridge, running roughly 2,000 kilometers from the coast of Chile toward Easter Island, had been known to exist for decades. Charts showed its outline. Sonar had traced its general shape, but no one had ever properly looked at it. No ROV had descended to its slopes. No camera had seen what lived there. The scientists aboard expected to find something. A few new species, some interesting distribution records, the careful incremental progress of deep-sea science. What they found instead changed the conversation entirely. In less than 30 days, working across 10 seamounts at depths of up to 4,500 meters, the team documented 100 species never previously recorded by science. 100. New corals, new glass sponges, new squat lobsters, new sea urchins, new jellyfish, new siphonophores, those extraordinary colonial organisms that exist somewhere between a single animal and a coordinated colony of thousands. Dumbo octopuses hovering near the summit with their characteristic ear-like fins. A deep-sea dragonfish, an apex predator with enormous jaws filled with fang-like teeth ascending from below. And while the ROV was mapping the seafloor, 4 seamounts appeared on the screen that were not on any chart. Mountains that no one knew existed, rising thousands of meters from the ocean floor, simply waiting. One of the newly measured seamounts, named Kahlewai, turned out to be almost 1,000 meters taller than any previous estimate. 1,000 meters. Taller than the tallest building ever built by human hands. And we had simply been measuring it wrong. For decades. The lead scientist, Dr. Javier Selenes, described the results as far exceeding their expectations. He said, you always expect to find new species in remote, poorly explored areas, but the amount we found, especially for some groups like sponges, is mind-blowing. When a researcher encounters what appears to be a new species, it is not simply declared new on the spot. Specimens must be collected, brought to surface laboratories, examined under microscopes. DNA must be extracted and sequenced. A formal scientific description must be written, peer-reviewed, published, and only then is a species officially named. This process takes months, sometimes years. The scientists involved have stated that the final number of new species, once the laboratory work is complete, will almost certainly be higher than 100. For most of human history, the deep sea was simply inaccessible. Even 50 years ago, visiting a seamount at 3,000 meters depth required extraordinary resources. Today, remotely operated vehicles have transformed what is possible. Here ROVs can descend to depths that would crush any human-occupied vessel. They carry high-definition cameras, manipulator arms that can collect specimens with extraordinary delicacy, and increasingly an environmental DNA sampling systems. A water sample collected at depth can now be analysed for the DNA of every organism that passed through that location in recent days, without catching a single animal, without disturbing a single coral, simply by filtering the water and reading what the ocean has written in it. Of the estimated 100,000 seamounts on Earth, fewer than 300 have been explored in meaningful detail. 0.3%. Less than 1/3 of 1%. Scientists estimate that the deep sea may contain anywhere between 500,000 and 10 million species that have never been identified. Never seen, never named, never studied. Organisms that may have evolved unique biological compounds that could have applications in medicine, in materials science, in biotechnology, that we will never know about. Because we never looked. Or worse, because by the time we look, they are already gone. In February 2026, a newly discovered deep-sea creature went viral on YouTube. A deep-sea cleton, a type of marine mollusk found nearly 3 miles below the surface. The public was invited to name it. More than 8,000 name suggestions flooded in from around the world. 11 different people, independently, without any coordination, suggested the same name. Ferreraella populi. Of the people. A creature found 3 miles below the surface of the ocean, named by the internet. In Latin, with unanimous agreement. 100 new species in 30 days. 4 previously unknown mountains. A creature named by 8,000 strangers on the internet. The age of discovery in the deep sea is not over. It's barely begun. But here is what keeps some scientists awake at night. The same mountains that hold these extraordinary ecosystems, the same slopes where 600-year-old coral grows in the dark, are also sitting on top of something that the modern world desperately wants. Something worth billions of dollars. Something that mining companies have been quietly planning to extract in 4 years. And the window to stop them is closing. Chapter 7. The Reckoning. Pick up your phone. Look at it for a moment. That glass, in that metal casing, that battery inside, the one that powers everything. It contains cobalt. Almost certainly. Cobalt mined from somewhere on this earth, processed, refined, built into the device you hold in your hand every day. The electric car that governments around the world are pushing as the solution to the climate crisis contains cobalt. More of it. Far more. A single electric vehicle battery requires roughly 10 kilograms of cobalt. The global demand for cobalt is projected to increase by more than 400% by 2050. And some of the largest deposits of cobalt on Earth, along with manganese, nickel, copper, platinum and rare earth elements, sit in thick metallic crusts on the slopes of seamounts. Right where the coral gardens grow. The metallic crusts on seamounts form through a process called hydrogenesis, minerals precipitating out of seawater onto the hard surface of the volcanic rock over millions of years, growing at a rate of 1 to 5 millimetres per million years. These crusts form carpets of metal-rich material roughly 30 centimetres thick across the seamount's surface. They are found at depths of 600 to 7,000 metres, rich in cobalt, sometimes containing concentrations 3 to 4 times higher than any land-based deposit. The minerals we need to build the green energy future sit on the slopes of the most biodiverse mountains in the ocean. Remotely operated mining vehicles can now be deployed to seamount slopes. They scrape the metallic crust from the surface of the rock, pump the material through a riser pipe to a surface vessel, process it, and send the waste back into the ocean. Several companies have already obtained exploration licenses from the International Seabed Authority. Exploratory surveys have been conducted. Test extractions have taken place. The commercial mining of seamounts, while not yet operational at the scale, is not a distant hypothetical. It is a near-term possibility. Return to the coral garden. The cold water coral that has been growing on that volcanic slope for 600 years. The glass sponge field that took centuries to establish. A mining vehicle scraping the metallic crust from the seamount surface does not avoid the coral. It cannot. The coral grows on the same rock that holds the crust. The sponges anchor to the same basalt that contains the cobalt. To take the mineral is to destroy the ecosystem. Completely. Immediately. Irreversibly. A coral growing at 1 millimetre per year, scraped away in a single pass of a mining vehicle, will not recover in any human timescale. A glass sponge field established over centuries, gone in an afternoon. The process of extracting minerals from the seafloor creates enormous sediment plumes. Clouds of disturbed material that billow outward from the mining site, carried by the deep ocean currents for hundreds of kilometres. Smothering filter feeders, clogging the feeding structures of sponges and coral polyps. Introducing toxic compounds into the food web. The damage from a single mining operation, though, extends far beyond that seamount. It extends into the network, into the stepping stone corridors, into the migration highways that whales and sharks have followed for millennia. There is an irony at the heart of deep-sea mining that scientists find almost unbearable to articulate. The minerals we need to build solar panels, to construct wind turbines, to manufacture electric vehicles are being sought in an ecosystem that is one of our most significant carbon sinks. Experts who have studied this question carefully have concluded that the clean energy transition can be achieved without deep-sea mining. Through improved battery recycling, through alternative battery chemistries that reduce or eliminate cobalt dependence, through more efficient use of materials already above ground. The mining of seamounts is not a necessity. It is a choice. More than 700 marine scientists have signed an open letter calling for a moratorium on deep-sea mining. The 30 by 30 campaign, the global initiative to protect 30% of the world's ocean by 2030, has placed seamount protection at the centre of its agenda. And the expeditions keep going. Because every new species documented, every new coral garden photographed, every new glass sponge field mapped, is an argument. A scientific, evidential, irrefutable argument that what exists on these mountains is worth more than the minerals beneath them. The decisions that will determine the fate of seamount ecosystems are not being made in the deep ocean. They are being made in boardrooms, in government ministries, in international regulatory bodies, by people who, in most cases, have never seen a deep-sea coral garden. Awareness matters. The story of seamounts needs to be told widely, repeatedly, to as many people as possible. If this documentary has moved you, share it. That is not a small thing. That is how the conversation changes. The threat is real. The window is narrow. But there is one final chapter to this story. Seamounts are doing something else. Something quiet. Something invisible. Something that affects every person on Earth, whether they know it or not. They are helping to regulate the climate of this planet. Scientists are only beginning to understand how. That story is next. Chapter 8. The Carbon Keepers. There is a conversation happening right now in laboratories, in research institutions, in the pages of scientific journals that has not yet reached the wider world. A conversation about carbon, about climate, about the ocean's role in keeping this planet habitable. Most people know that forests absorb carbon dioxide. The Amazon, the boreal forests of Canada and Russia, the ancient woodlands of Central Africa, them. We talk about protecting them. We plant trees. We measure their carbon storage capacity in careful scientific units. But the ocean absorbs more carbon than all the world's forests combined. More. Significantly more. The ocean is the largest carbon sink on Earth, and seamounts are a critical and underappreciated part of how it works. Carbon enters the ocean at the surface. Carbon dioxide from the atmosphere dissolves into seawater. Phytoplankton at the surface absorb it, using it for photosynthesis just as land plants do. When they die, they sink. Along with the organisms that ate them, and the organisms that ate those. A constant rain of the organic material, scientists call it marine snow, drifting downward through the water column, carrying carbon with it, down, away from the atmosphere, into the deep. Seamounts, by concentrating biological activity through upwelling, enhance this process. More life above the seamount, more marine snow falling from it, more carbon locked away in the deep. Whales are, among many other things, extraordinarily efficient carbon storage vessels. A blue whale may weigh 150 tons. Much of that mass is carbon. When a whale dies naturally and sinks to the ocean floor, where that carbon goes with it. Down into the deep, away from the atmosphere, potentially for centuries. A single large whale fall can sequester the carbon equivalent of thousands of trees. And whales congregate around seamounts. When they die, many of them die in the vicinity of seamounts. Their bodies sink to the slopes, adding their carbon to an ecosystem that is already one of the ocean's most significant biological carbon stores. Glass sponges and other filter-feeding sponges on seamount slopes process enormous volumes of seawater. They absorb dissolved organic carbon and convert it into sponge tissue and waste products that large animals can consume. This transforms carbon that would otherwise drift through the ocean unutilized into biomass, into the food web, and eventually through the rain of organic material to the seafloor into the sediment, locking it into the deep ocean ecosystem, away from the atmosphere, for decades, for centuries. Seamount ecosystems, the coral, the sponges, the biological communities on their slopes, represent a measurable contribution to the ocean's carbon sequestration capacity. A contribution that is currently unaccounted for in most climate models. A contribution that would be, permanently and irreversibly, eliminated by large-scale deep-sea mining. Step back now from the individual seamount. Consider the system as a whole. 100,000 underwater mountains distributed across every ocean basin on Earth. Each one concentrating biological activity. Each one enhancing the biological pump. Each one contributing to the sequestration of carbon in the deep ocean. The seamount is not just a mountain. It is not just a biodiversity hotspot. It is a component, an active functioning component of the Earth's climate regulation system. A system that has been running, or without interruption, for tens of millions of years. Long before we understood it. Long before we even knew it existed. The news about seamounts is not only difficult, it is also genuinely hopeful. The science is accelerating. Every year, more expeditions, more ROV dives, more species documented, more of the network mapped and understood. The global conversation about protecting the deep sea is growing louder. And the expeditions themselves, the images they return with, the species they discover, the coral gardens they reveal, are doing something that scientific papers alone cannot do. They are making people feel something. About a world most of them will never visit. In a darkness most of them will never see. On mountains most of them did not know existed. That feeling of curiosity, wonder, protectiveness towards something fragile and extraordinary is not nothing. It is the beginning of everything that matters. There is a seamount in the South Pacific, an unnamed, yet unvisited, that has been standing in the dark for 80 million years. On its slopes, almost certainly, there is coral. Centuries old, growing at 1 millimetre per year, in cold water that has never been touched by sunlight. There are glass sponges filtering that cold water, their silica skeletons glowing faintly in the dark. There are brittle stars reaching upward from the coral branches, arms extended into the passing current, waiting. And somewhere in the water above it, following the seamount chain as their ancestors have done for thousands of generations, a whale is passing. It does not know we are thinking about it. The seamount does not know we exist. But somewhere above it, people are beginning to understand its value, are beginning to fight for it, are beginning, slowly, imperfectly, but genuinely, to care. That is where we are. That is what tonight has been about. Now, it is time to rest. Outro. Rest. Beside the mountain. We are done learning for tonight. There is nothing more to understand. Nothing more to hold on to. Just this. The ocean. Dark. Cold. Still. Somewhere far below the surface of the world tonight, a seamount stands in the dark. As it has stood for millions of years, patient beyond any measure of patience we carry in our human lives. The current moves past its slopes. Slow. Cold. Constant. Let your body sink now into whatever is beneath you. Let the weight of the day release. You do not need to hold anything right now. On the slope of the seamount, the coral garden sways. Imperceptibly, the brittle stars have their arms extended into the current, reaching, waiting. They do not know about the sun. They have never needed to. Breathe in slowly. And out. A glass sponge stands on the volcanic rock, filtering the cold, dark water. It has been standing there for longer than any living person has been alive. There is something deeply restful about that thought, about the existence of things that simply persist, that do not rush, that do not worry, that simply grow. Millimetre by millimetre, century by century. Let your breathing slow. A little slower still. Match the rhythm of the deep ocean current, which is in no hurry to arrive anywhere. Somewhere on the seamount, a Dumbo octopus hovers, its fins moving with a slow, unhurried rhythm. Up, down, up, down. It is simply present, in the dark, in the cold, above a mountain that has been here since before memory. Release the thoughts that are still moving through your mind. You do not need them right now. They will be there in the morning. But tonight, for these hours, it can wait. The seamount does not think about tomorrow. The coral does not plan for next week. They simply are. Let your eyes be heavy now. Now. The weight of sleep come. Today is done. The seamount will be there in the morning, as it will be there in 100 years, in 1,000, in 1,000,000, if we are wise enough to let it. Rest now. You are safe. Adil. Good night.